So, hi everyone, thank you for coming. Today we're going to talk about functional programming. More specifically, we're going to see how we can do PureFP with legacy code, even without modifying it. Before we start, a quick show of hands. Who's here has never done PureFP before? PureFP? Okay. Okay. Let's start. So a little word on who I am. So I'm a backend developer at Liso Group. It's a French company. It specializes on data processing, especially in the tire business. So I've been a Scala functional developer for 2 years now. Before that, I was a Java and C# programmer. And during that time, I had the opportunity to migrate non-PureFP code to PureFP code, and that's exactly what we're going to talk about today. Today we're going to see how we can migrate our code, our legacy code, into PureFP code. So we're going to see why we as developers would take that effort. We're going to see why our employers should let us take that effort, and we're going to see how we can do it painlessly. We are also going to see how we can interrupt with legacy code. When should we migrate code? When should we interrupt with legacy code? And especially, how can we interrupt with side-effecting legacy code? And then from there, we're going to see where we can go. Before we start, a little word on legacy code. What is legacy code? Here, we're going to assume that legacy code is code that existed before in your project. Whether that code is tested or untested, whether it's simple or complex, whether it's code that you have written or that was written by someone else, it doesn't matter as long as this code is not pure. So let's start with functional programming. I guess most of you already know what functional programming is. So functional programming is a declarative programming paradigm in which you program with functions. But not just any functions. In PureFP, your functions must be total, deterministic, and pure. They must be total, meaning that for every possible input, you must have one single output. Deterministic, meaning that every time you call your functions with the same input parameters, you should always get the same results. And pure means that when you call this function, there should be no side effects. And when you run a program in functional programming, you're actually evaluating an expression and interpreting its results. And those properties I just cited, well, they lead to predictability, to predictable code. In PureFP, function signatures don't lie. If a function signature says that the function takes a string and returns an integer, then you can call it with your name, you can call it with an empty string, you can call it with an entire collection of Shakespeare, you will always get an integer. But it also comes with other benefits. It also comes with equational reasoning, thanks to reflection transparency, meaning that you can always replace a function call with its result. That won't affect your program. And it's also easy to test. When you want to test a PureFP code, you just call it with some parameters, and you just have to check that the result is the one that you expected. And also, PureFP code is easy to change, because most of the unintentional mistakes that you can make, the compiler will catch them. But today, we are going to focus on a specific language. We're going to focus on Scala. So Scala is a JVM language. It's a fusion of functional programming and object-oriented programming, and it is oriented towards practicality. Also, it has a very large ecosystem. This ecosystem contains 3 major categories of tools. The first category of tools are PureFP tools. I think most of you already know CATS and Scala Z, but there's also an ever-increasing number of tools that are pure. For example, if you want to build a web service, today you have HTTP4S. If you want to do JSON serializing, today you have CSS. And if you want to do stream processing, you have FS2. But then there are also other category of of libraries, and this library is every single Java library. Because Scala is a JVM language and is capable of interoperating with Java, you can use every Java libraries that exist. And Java is very widespread. For everything that you need to do, there's the highest chance that there's a library out there in Java doing just that. For example, if you want to use a relational database, there's a high probability that we will find a JDBC driver for it. And so that leaves us with a third category of libraries, which is actually everything in between PureFP tools and Java tools. For example, there's the Arca libraries, and there are the Play frameworks. They are built in Scala, but they're not really that pure. And also, theoretically, because Scala is based on the JVM, you could also theoretically use any libraries that is coded in a language that is based on the JVM. And so that leads us to an opportunity for reusability. Whether the code is pure or legacy, you don't have to reinvent the wheel every time. So you can reuse existing code and yourself focus on the business needs. And if we take reusability, simplicity, and predictability, then we have productivity. When you have a new member on your team that comes into your project, they can be productive very quickly. Okay. Now that's all great, but are there any downside? Well, there are some hurdles. We are basically talking about a paradigm shift. We are talking about going from a non-pure FP paradigm to a pure FP paradigm. Sounds complex, sounds risky, with a high risk of regression, but we will see today that there is a method to achieve such migration without much effort and with a low risk. Also, there's another problem with this code ownership. If you own the code, then you probably understand it, and you can probably modify it, so it's easier to migrate. But what about code that you don't own? What about code that you cannot change? Well, we will see that code ownership is not a prerequisite for its migration. And that's what we are going to see right now. So let's start with code that we own. Now, because it's code that we own, we can modify it. So we think that, well, it should be easy. Maybe we can just rewrite it once in pure code. But it turns out it's not so practical. Depending on the size of your project, it can take lots of time. Depending on the complexity of your project, it can take lots of efforts. And if it takes time, maybe it will block any new features to your project, which is problematic. But we will see a method, a step-by-step method that allows us to migrate our code without much effort and without much pain. And to show you this method, we're gonna take an example, a very simple example. Let's imagine that we work for a small modern art gallery. Now, this small modern art gallery has a process called work of art qualification. Basically, it means that it's going to produce an objective ratings based on expert ratings and user ratings based on some coefficients. You don't need to understand this, it's just an example. It's just an example of legacy code that we want to migrate. Now, how does the code works? Well, you have here you have the entire pipeline. First, it's a workflow. That first collects all the user ratings from a CSV file. It passes those ratings. It groups them by work of arts. It tries to match them on works that are already known and for which we already have an expert ratings. Then it does the qualification with some coefficients, and then it indexes those in a search engine, in this case Elasticsearch. So this is an example of a legacy project that we want to migrate, and you can see here that there are lots of side effects. Looking at the domain, we have several IDTs. So you don't need to read everything. What's most important here is that we have some work of art that is identified by an ID that is associated with the expert ratings. The expert ratings contain score along 3 different criteria: a general criteria, an originality criteria, and colors criteria. And then a qualified work is just a work of art that has some objective ratings. And to compute these objective ratings, we use some qualification coefficients. Now, what we want to do is migrate our qualification process. Now, maybe you have also noticed there are some other flaws in this domain, but right now we're going to focus on the qualification process. Okay, what is this step-by-step method? It's a method that is mechanical and iterative. It is composed of 4 steps. The first step is the planification. What code do we want to migrate? What's our current objective? How will it benefit me? Then comes the second step, test. The second step, test. How do we guard ourselves against regressions? Is the code that we want to migrate tested? If it's not, how can I make sure that I won't introduce any regression? Step 3 is build. Okay, now that I know what I want to do during this migration, how am I gonna do it? What's the appropriate function signatures? What is the appropriate domain model? How am I going to implement it? And then the final step, step 4, is refactoring. How can I inject my new code into the existing code? But that's the overall migration method. And for every method, we have tools. Well, the tools for this migration, you already know them. An IDE. The IDE will be of major help when you want to do refactoring. It's going to help you extract functions. It's going to help you extract variables. It's also going to help you rename things. And sometimes it's going to help you spot mistakes in your code. But it's not perfect, and that's why we have the compiler. The compiler will catch any mistakes that you can make and explain it to you. And finally, we need to have a test framework. The test framework is going to be used for regression testing. And it's also going to be used to test that the code that you are building, the pure functional code that you are building, also suits the business needs. So if that's all okay with you, let's start. Let's start with the planification step. So during these steps, we're going to choose what code we want to migrate. And to choose the code that you want to migrate, it all depends on your priorities. Now, good first candidates would be code that changes frequently. Or another good candidate would be code that is prone to bugs and regressions due to complexity, for example. And another good candidate would be critical business code that is not tested. Okay? So now that you have chosen your code to migrate, now you're going to have to ask yourselves what you want to do during this small migration step. Do you want to refine the model? Do you want to rewrite business rules to be pure? Or do you want, for example, to isolate business code from technical code? If you don't know what should be your current migration objective, let's try something. Let's take a step back and let's see the larger picture. Imagine a legacy project. If you're unlucky, it might look like this. It might look like a blob of components, and in each component, you're going to find business code entangled with technical code. And in those components, you're going to find impure code everywhere. So that would be code with side effects. So, okay, that's if you're unlucky. But then, what would be the ideal architectural design for an FP project? Well, there are many architectural design compatible with pure FP. There is the onion architecture, there is the hexagonal architecture, and so on. What they all have in common is the separation of concerns. Now here, we'll take as an example the hexagonal architecture. Notice that we have three different layers. You have the domain layers that should contain your business logic, and those business logic should only be represented by pure functions. And also, another layer would be the application layer. The application layer will contain the logic that is facing the user. For example, it would contain code that would be a web service, or it would be a CLI application. And there's also the infrastructure layer. Now this layer will contain all the logics that will support your domain and application. For example, it will handle everything related to data storage or such engine activities. And in both the application and infrastructure layers, we also need pure code. But sometimes you're going to need impure code. How do we deal with those? Well, we wrap them inside what we call effectful functions. Now, effectful functions, we're going to see that later on. But the most important thing here is that every side effect must be pushed toward the end of the world. The only place where you should do an unsafe call to do side effects should be at the start of your program. Okay, now that would be the ideal FP architecture. How can we go from the blob of components that you just saw to this architecture? Well, on the large picture, we have two big major steps. First, we want to isolate logic. We want to isolate business code from technical code. And with the hexagonal architecture, we will go one step further. We want to separate application logic from infrastructure logic. And as for the impure code, what we want to do is migrate to transform impure code into pure function. Now, if that's possible, we'll transform impure code into pure functions, and if this code must have side effects, then we're going to convert it into an effectful function, wrapping the impure code. And once we've done that, there's one last step, that is just redistributing every component into the appropriate layers. So in the application layer, the domain layer, or infrastructure layer. One thing to remember though is that the domain layer must be independent. Only the application and infrastructure layer can depend upon the domain layer. But that's great. That's what we want to do in the large scale. But how does that translate for us? So if we come back to our walkabout qualification process, what we want to do here is purify, if I can say so, our qualification process. And this qualification process in our code, it looks like this. So this is an ACA stream workflow. You don't have to understand ACA stream, that's all right. What we can note though is that the qualification process is right here. It's deeply nested inside technical code, inside ACA stream code. And that's why we want to extract it into a pure function so that we can test it, can modify it predictably. Okay. So right now, in the plan step, we have decided that we want to migrate this piece of code, this qualification piece of code. So okay, we have our objective. Now, what can we do to make sure that we won't introduce any regressions? Now, what we want to do here is check whether the code that we want to migrate is covered by test. If it's covered by test, exhaustive test, then okay, we can skip that test. However, if it is not, just like our qualification example, how can we make sure that we won't introduce any regression? Especially, we don't want to introduce any regressions while we want to test it. So when we look at how the pipeline is run, the code looks like this. We have a class named pipeline, which defines a method, run pipeline, which, well, execute the pipeline. But looking at this code, we cannot just test the qualification process. If you want to test the qualification process, you have to run the entire pipeline. So what can we do here? Unfortunately, there are no universal methods. It all depends on your project. But here, in this case, what we could do is replace. Well, we can try to use test data. Use specific test data throughout the regression test. And as we see, what we see is that the ACA-stream workflow loads the CSV file called ratings.csv inside the current directory. So what can we do here? We can actually just run our regression test inside our testing directory. And that would mean that we would be using our regression testing data. But we also have here, it looks like we are loading the qualification coefficients from disk, but we don't know how, from where, and etc. However, this is actually a method in the same class. So what we can do is create a subclass of the pipeline classes and overriding this method. And that would allow us to write this regression test. Here, what we are doing is we are using the test container libraries to create a temporary Elasticsearch Docker container. And then we can create our new test pipeline inside our testing directory to load the user ratings data from our regression tests and execute the entire pipeline. And then the pipeline, what it will do is index the results inside our Elasticsearch container. All is left for us to do is check whether the results that were indexed were the one that we expect. And what would be the data that we expect? Well, it would be the first data that we get from the first execution of the pipeline. It would constitute the golden master of our regression test. And when each and every time that we make a modification in our code, we can run the regression test and check whether the results matches the golden master. If it does, then we can be somewhat sure that we haven't introduced any regression. If it doesn't, then we have made a mistake somewhere and we are going to need to roll back our last modification. And that's how we can make sure that we won't have any regressions. So comes step 3, which is build. In the build step, we're going to see depending on the current migration objective, the appropriate function signature or domain model. If we want to rewrite a business rule to be pure, then we're going to start by defining the appropriate pure function signature. And if we want to refine the data model, then we're going to define the right target model. And once we have built this template, we can then implement it. So remember that in a pure FP, every function that you make must be pure, total, and deterministic. Coming back to our qualification process, if you remember, the qualification process needs to produce a qualified work. A qualified work needs a work of arts and the objective ratings. The objective ratings are computed by applying the qualification coefficients on both the expert ratings, the user ratings, and the qualification coefficients. So looking at this code, we can deduce that the appropriate function signature here would be, for example, a function named qualify work with the qualification coefficients, a rated work, and it would produce a qualified work. Okay, so now we have our pure function signatures. How can we implement it? You have several ways to implement this code. You can either extract the code and write some tests to make sure that the code that you've extracted suits your business needs, or you can rewrite it completely using a different method, for example, TDD. Now, I won't go into TDD, there are plenty of documentation out there, but it's just to show you that there are multiple methods with which you can write pure code. And so our final code would look like this. Now, okay, now we have a new pure function, functions. What's left for us to do? Well, now that we have it, we have to use it. And that's what the final step, the refactor step, is for. During that step, we're going to inject the new code into our existing code. And now you have multiple ways to do it. You can either directly replace every occurrence of the old code with the new code, but sometimes that can be cumbersome. Maybe there are several occurrences throughout your code. So another method would be to modify your existing code to actually call your new code. Fortunately for us, the qualification process just takes place once. So it's rather easy. We just have to replace the old code with the code to our new functions. And then we are done with migrating the qualification process. Now you might tell me that, yeah, that was great, but you just took a very simple example. How do we deal with a more complex example? More specifically, how do we deal with side effects? Well, the method that we just saw still applies. It's just that you won't have pure functions like that. You will have to use an effectful function. Now, what's an effectful function? An effectful function will look like this. It will return an effect. And what's an effect? An effect is an immutable value that models the side effects. Now, you probably already know most of the effects here. Here we have the mostly used effects in legacy code. So you have option that models functions that may or may not return an answer. You have either that models function that may fail with an error. You have list if your functions can return multiple answers from 0, 1 to as many as you want. And then you have IO that models any side effects. So how do we use them? Well, for each of them there is a use case. Let's imagine that we want to migrate a partial function. So what's a partial function? A partial function is a function that may not have an answer depending on your input values. For example, here we have a function that takes a score value as an integer, but it will only accept integer values that are between 0 and 5. And when it fails spectacularly with an exception. But then in legacy code, such code could throw an exception or could return no. So how do we handle those? Well, I think most of you already know the answer. We use the option monad. So if we have a value, we wrap it inside the sum. If there is no value associated with the input value, then we return none. So that's an easy case. Another easy case is how we handle errors. Now, legacy codes usually handle errors by throwing an exception or returning no. Well, in pure FP, that would be a big no. A big no, because that would mean your function signature lies. So how do we handle that? We handle that with an either or an option. So the option way, we have already seen it previously. And for the either way, you just have to have an either to specify the type of errors that you can get and the type of result that you can have. And if there's an error, instead of throwing an exception, you just return a left with the reason for the error. And if the computation succeeded, then you just take that value and wrap it inside the right. So I'm going very quickly on those because I think you already all know how to use those data types. What's most interesting here is how we handle side effects. So what is side effects? Side effects are everything that breaks referential transparency. So that's everything that interacts with the real world, to put simply. And to handle those, to handle impure code, impure side-effecting code, what we have to do is wrap it inside a specific data type, and this data type is I/O. Now, unlike Haskell, Scala doesn't have a built-in I/O. You have to provide one for it. Unfortunately, there are many implementations. You have Cat's I/O that provides a basic reference for I/Os. You have Monix that provides way more advanced features for I/Os. And then you have Zio, the new kid in town, the challenger, that has way more features, I/O features, than the other two. But if you are interested in any of those three, I'll encourage you to read the documentations. Today, I'm going to focus more on Cat's I/O. Why Cat's I/O? Because as I said, Cat's I/O is a basic reference. So everything that you can do with Cat's I/O, you can do with the other two pretty easily. So coming back to our example, how do we handle impure code and side effects? We just have to wrap them inside an I/O. And to do that, we'll use the function delay. For example, here, when we get the current time, now this needs to interact with the real world, so it's side effecting. So to wrap it inside an I/O, you just have to call delay. And that will wrap the impure code inside an I/O neatly so that you can work with it later. If you already have pure values, you just have to call I/O pure. And if you already have an exception, an error, you can also wrap it directly with raise error. Okay, so with everything that we've seen so far, you have everything that you need to migrate the code that you own. But then, what about code that you don't own? What about code that cannot be changed? Example of code that cannot be changed would be code from third-party dependencies, or it would be code from another team, or we can even go further. It could be legacy code that is too complex and you believe it's not worth the effort of migrating. So what's the problem with code that you cannot change? Can't we just use what we've seen so far? Well, you could, but there are multiple issues. There is an interfacing problem. For example, maybe the impure code will forces you to do impure code by doing mutations on your parameters. Maybe it forces you to use complex control flows like side-effecting callbacks and such. And then there's a pollution problem. Because you use impure code, it will forces you to use impure code. For example, with futures. What's wrong with futures? Well, the problem with futures is that it is eager, meaning that once you have a future in your hand, it is already running, or it has already done running. And that is a big side effect. Another problem with future is that to work with one, you need an implicit execution context all around your code. And that is just a very big pollution problem. And the issue with futures is that there are lots of libraries that requires you to generate one. And there's also the other case where the libraries might require you to extract the result from a future, and that's problematic. So how can we handle those? Well, the first, to handle those, handling those is a two-step solution. It's a two-step solution. The first step you already seen. You just wrap your impure code inside effect types, and then, depending on the case, you are going to need to use dedicated combinators for each use case. What use case? Let's see some of those use cases. You have synchronous calls, for example. What's a synchronous call? A synchronous call is a call to a method that will only give you back control when it has done computing the results. That means that those kind of calls will be executed sequentially. How do we deal with those? Well, you already know the answers. We just wrap it inside an I/O. And is this it? Well, yes and no. For most of the time, it will be enough. But for a specific category of synchronous call, there would be problems. And this category of synchronous call is the blocking calls. Blocking call is a synchronous call that actually blocks and waits on something, on some event. For example, it could be waiting for you to type something on the keyboard, or it could be waiting for a message on the network. In any case, it waits for something, and while it is waiting, well, it doesn't do anything else. So how do we deal with those calls? Well, we can deal with it by not dealing with it, meaning that we just ignore the fact that they are blocking. In our example here, we try to read something that the user will write on the keyboard. Now, this is our blocking call, and then when we got the result, we just print it. Okay, so what's the problem here? The problem here is that you are effectively underusing your CPU. Why? Because all the I/O libraries that we've seen so far, so CATS.io, Monix, and Zio, what they do is they actually optimizes the engine to have at most one I/O per CPU core. So that means that you're going to have the I/O computation, here the read line, that is using a single CPU core, well, to do nothing. And that means that there's one less core for all the other I/O computations to actually do real work. So how can we handle those situations? Well, with CATS, you're gonna have to do it manually. And to deal with those calls, you're gonna have to use a specific thread pool. You're gonna need to have, for example, an unbounded thread pool that will contain all of your blocking calls. And then you're going to need a context shift. What's a context shift? It's a data structures in CATS.io that allows us to tell CATS in which thread pools we want to execute our I/O. Right here, like we said before, we know that readname is an I/O that does some blocking. So how do we tell CATS to actually execute it in a dedicated thread pools? Well, we just use context shift, and we tell context shift that we want to evaluate this blocking I/O inside these specific thread pools. And will that solve our problems? Yes.
Is this the equivalent of effect async in Zio?
I will come back to that. And what this does is it tells CATS that we want to execute this blocking I/O inside this specific thread. And it also means that the default CATS thread pools will be available to other I/O computations that will do real works. Now, just like coming back to Zio, just like you said, is there a simple way to do this in CATS? Not really. However, with Zio, there is a simple way. You just define your I/O in Zio. I/O are called tasks. In Zio, you just have to define your I/O just like you always do, and then to tell Zio that this I/O is blocking, you just have to call the blocking functions in the blocking API, And that effectively tells ZIO that this IO is blocking and that it has to use a specific thread pools dedicated to blocking calls. And then ZIO will handle it for you. You don't have to create your own thread pools or anything else. The ZIO will take care of it. I hope that answers your questions. Now, we've seen synchronous calls. What about asynchronous calls? And synchronous calls are calls to methods that give you back control before the result has been computed. And to give you back the results, it will call you back in a specific way. Now, in legacy code, there are two major ways to do asynchronous call. There is the Scala future, and then there are callbacks. So using future, like I said before, there's a problem with future. Future is eager. We need to stop this eagerness. And to stop this eagerness, just like any side effect in code, we just wrap it inside an IO. But then there's another problem. This piece of code would actually have a type of IO of the future of something. Well, and to extract the value out of the future, you just have to call from future. What it does is, actually, when it has to execute the future, it will do so and then extract for you the value inside the future, or the failure if the call has failed. And then if you know that you have a successful future value, you can directly use IO pure, and same goes for errors. Then what about callbacks? Now, callbacks happens very frequently in legacy code, especially in Java legacy code. In those cases, imagine that you have a legacy client that can send a request over the network. And when it has an answer, it will call you back with it so that you can act on it. So how do we handle those cases? To handle those cases, we have IO async. And what IO async does is that it calls you back, providing you a cat's callback that you can call with the results of your legacy call. And here, what we can do is we wrap we call our legacy method with a custom callback, and this callback, when we have extracted the results, we can send it back, we can feed it back into cats using the cat's callback. If the call has succeeded, we have to wrap it inside the right. If the call has failed, we wrap it inside the left. And then, by doing this, the result will be the IO of the expected type. And that's how we can handle legacy asynchronous calls. So there's also a way to automatically manage resource allocation and release. In other words, to migrate the try-finale blocks. Since I don't have much time, I'm going to go through services. Services, how can we migrate impure services into, pure services? For example, we have an akka stream, we have an akka stream function, and this akka stream function does a lot of things. You can see right here that we have a lot of technical akka technicalities. We have to use a specific akka API to load the CSV file. We have to use a specific akka method to handle the CSV parsing. And inside all that, we have some business code. Sometimes we have to specify technical details such as parallelism levels. And so we can have some code that is entangled between business codes and technical code, and that complicates things. Why? Because if we want to change implementations, if we want to use another stream processing libraries, that, well, we're going to have to rewrite our business code. And some goes the other way. If we want to rewrite our business code, we're going to have to mess with this infrastructure. So how can we deal with that? Well, we can consider the service as an ADT. And then we can have functions that will interpret this ADT and do everything that is required behind the scenes. For example, here, what we can do is declare our own ADT that represent the service. Here, the service that we want is actually a workflow, and everything that you have in this ADT will only be business-related parameters. And in this way, you would have separated business complexity, the business complexity here, from the technical complexities. And that would mean, first, some clearer code. It would mean that your code would be more testable, because you have separated business from the technical details. You can easily test one or the other separately. But it also means that your code would be more modular, because you can then easily switch implementation when you need to. A small break. Sorry. And that leaves us with one last thing to see, which are frameworks. Why are frameworks a problem? Well, frameworks generally handle all the bootstrapping for you. They will start as your program starts, and it will only give you back control at certain points in times. For example, for the Play framework, it will only give you control once you have received an HTTP request. And unfortunately, that means that we have control at this point. And at this point, all you can do is generate a future. So what we can do, well, to produce, you can still write your function to be as pure as possible with IOs and everything, but you have to consider the framework as a new end of the world. And because it's a new end of the world, then it's only at this point can you do unsafe calls. And in this case, the unsafe calls is producing a future that will give you back to the Play framework. Okay. So I don't have much time left, so to go beyond. Now, what we have seen so far will allow you to do pure functional programming with legacy code, but with very basic functional blocks. Now, there are more advanced functional building blocks, such as algebras, type classes, and sometimes more advanced types, such as refined types and everything. You could use those. Your code will then be more concise if you know how to use those functional constructs. I encourage you to see those different constructs, and if you have any questions on them, I can answer those right after the presentation. The refined types, well, I don't have that. I will let you see that for yourself. There are also more advanced tools out there, so I don't have time to present right now. Some interesting tools. You can use plugins such as Word Remover, which will allow you to check that the code that you are generating is actually pure. And there's also a useful plugin which is called Beta Monadic 4, which allows us to do various things, such as pattern deconstructing, like right here. So, okay, so there are many things that you can do with functional programming, but what we saw today, this.
So with the deconstruction for like option and list and the
the built-in monads in Scala, you can do that deconstruction, but you can't do it with the cat's IO, so you need the better forward for cat's IO and CIO to do that?
If I got your question correctly, you were asking if we can do that without the plugins?
So you can do the deconstruction without
Yes.
plugins
Yes.
for option and list and like the normal and future and like the normal
Yes.
Scala stuff, but you can't. So is this plugin for cat's IO? Like,
Actually, it's for any libraries, because why do we need these plugins? It's because actually when you do that in Scala, Scala requires you to have a width filter in your data type, and IO doesn't have this method. And so if you don't use these plugins, then your deconstruction will fail. And if you use that plugin, then it will work just like in option list and okay. Okay, so what we can take away from this presentation is that we can actually migrate any legacy code, even if it's side effecting, gradually. And in case that you cannot migrate your legacy code, you can always interrupt with it. And then if you have the courage, you can always read more about more advanced functional structures that would allow you to build more concise code. So I think that's all the time that I have. So thank you for listening to me.